So we're going to do a quiz on what I talked about on Wednesday at the end of class today. We're going to start talking about pressure today and maybe get into the first law of thermodynamics. So pressure. Oh, thank you. Okay, pressure. So when we talk about pressure, we're mainly dealing with, so this is mainly in fluids. And when I talk about fluids, I'm talking about both liquids and gases. And pressure is the force divided by the area that's applied perpendicular to any surface. So, for example, if you had a pressure vessel, like a spherical pressure vessel with a gas in it, and then inside you had an object like that. Okay, so the gas is all this here. Then a free body diagram of the sphere. Would look like this. At every point, that pressure is pointing perpendicular to the surface. And if you looked at a free body diagram of the object that's inside there, the pressure is applying forces perpendicular to every one of those surfaces like this. You have kind of like this vague sense that that pressure can be a force or suction can also be a force, but you need to kind of start getting your mind used to the fact that all there is differences in pressure, and all pressure can do is push on things. There's no such thing as suction. It's just differences in pressure. So like when you, like if you imagine sucking the air out of like nobody has a plastic pop bottle or whatever, but you can imagine if you suck the air out of an empty pop bottle, you feel like you're sucking the sides in. But what you're really doing is when it's sitting there, it's in an equilibrium, a tenuous equilibrium that comes from atmospheric pressure pushing in on the sides and the atmospheric pressure inside pushing out. And so when you remove air from the inside, you're lowering the pressure on the inside, and now the pressure on the outside just wins this battle because there's a lower pressure on the inside. So try not to think about suction as being a thing. Try to think about suction as kind of as being a case of two fighting pressures where one is losing. Okay. Same thing with like if a door blows off an airplane or a window or something. So in order for people not to die in airplanes, they pressurize the cabin. They don't pressurize it all the way to ground to ground atmospheric pressure, but that pressure is a lot higher inside the plane than it is outside the plane. And so if a door flies off, all of that high pressure air inside wants to get outside, and that's what takes things and people out the door of an airplane, you know. If a fluid is continuous and at rest, you can calculate the pressure due to a change in height this way. So the pressure at the lower height is equal to the pressure at the higher height plus the density of the fluid times G, 9.81 meters per second squared, times like the depth. I'm calling it H for height. So this rho is the density of the fluid. That's the mass divided by the volume. And G is 9.81 meters per second squared. If you're on the surface of the Earth, that changes a little bit as you get farther away from the Earth. One thing to notice about this equation is that it's easier to use with liquids than with gases. Because liquids are usually almost completely incompressible. So let's say because liquids are usually nearly incompressible, we're going to make that assumption a lot, that liquids are incompressible. And what incompressible means is that density doesn't change no matter what the pressure is. So the density is constant despite pressure changes. Gases are not incompressible at all. It's very easy just with the pressure you can apply with your hands. I mean, you can imagine like if you have a gasket sealed syringe, I mean, it has a gas in there and you can easily compress it to a smaller volume, which changes the density. And so if you're trying to use this equation with a gas, that density is going to change and you're going to have to do it using calculus and stuff, you know. But with liquids, it's really easy. All right, I want to ask one question just to make a quick point that I think is important to keep in mind always in your engineering classes. So here's the equation. It says that just based on the height difference between 2 points, if you know the density and stuff, you can calculate the pressure. Why doesn't this hold for these two cases? So the first one is, you know, like imagine a bike inner tube that's inflated. There's the valve. Uh, so in here, you have a very high pressure. At the same height here, you have a relatively much lower pressure. That doesn't look like it makes sense with this equation, but why doesn't it work here? So like, just remember that with any equation, the key is in the details. You know, don't just apply this equation. Like, or I guess any equation that you're using, be sure you know when it works and when it doesn't. The fluid has to be continuous for this to work, and so the fact that there's this barrier of an inner tube in between means that it doesn't hold. Okay. And so the second one, you can imagine if the first requirement is that it be continuous and the second requirement is that it be at rest, why doesn't it work in this case where you have like a fluid moving through a tube with changing dimensions? You have a high pressure here, a low pressure here, even though the height doesn't change.
Because the velocity would change.
Yeah, and the velocity doesn't even have to change. Just the fact that you have that this fluid isn't at rest means that you can't use this. But in this case, yes, the velocity would be changing too. Okay, so let's see this work. I guess I first did this example like when I was teaching this class right after the, remember the Titan submersible implosion. So let's just calculate the pressure and stuff. Before I do that, just erase example with your electronic pencil. Always be aware. Are you being given gauge pressure? How do you spell gauge? G-A-U? Gauge pressure or absolute pressure? In this class, for our calculations, we're always going to want the absolute pressure. And the relationship is that gauge pressure, well, let me write it as the absolute pressure is equal to the gauge pressure plus the atmospheric pressure. So gauge pressure is just how different you are from atmospheric pressure. Like a tire gauge measures things naturally in gauge pressure because all it can tell is the difference between the pressure inside the tire and the pressure in the air, you know. And so anytime you're given a pressure and gauge pressure, you want to add the atmospheric pressure to it to get the absolute. Okay. Okay, now example. So let's say that we have, so let's treat this Titan submersible as a stand-in for it. We're just going to have a 1 meter cube box. And it's going to be hollow. and it's sealed at sea level, which means that the pressure inside the box is atmospheric pressure. Okay. And we want to calculate, so first, what's the pressure at a depth of 3,800 meters. How many times atmospheric pressure is that? And then we want to calculate the net force acting on a single side. And we're going to use that atmospheric pressure. Standard atmospheric pressure is 1.01 times 10 to the 5th pascals. The atmospheric pressure fluctuates some around that, but that's usually at sea level what the pressure is. And we're going to use that, the density, well, I guess we'll use the density of fresh water, even though this is the ocean. I don't have the density of salt water written down, but the density of water is about 1,000 kilograms per cubic meter. So
Is the ocean higher or lower?
it's higher. Because the salt is denser than water. And actually, this is an interesting fact. You'd think, I mean, I should say, I was surprised to hear this. I would think like, okay, if you have a speedboat and you're going as fast as you can in fresh water and seawater, I'd think like, okay, maybe the salt increases the friction a little bit, and so it would be faster in fresh water than seawater. It's actually the opposite, because if you're, maybe in physics 1, you talk about buoyancy force. And so the denser a liquid is, the higher a floating object sits in it. And so in seawater, a boat sits higher in the water. It's not as much of it as underwater. So you have less friction because of that higher seating in the water. And so boats actually go noticeably faster in seawater than they do in fresh water.
Does it have an effect on like the friction per surface area?
You would think so, but I don't know that. I just know that the reason that it's faster in seawater is because the boats all sit higher, and so the overall friction is less, and that it's not a theoretical thing. It's like a thing if you take your boat, you're like, damn.
Well, is friction intermolecular forces at the micro scale?
Yeah.
Okay, so I would imagine it does, having that actually different.
You sure would think so, yeah. But it just isn't. It doesn't make up for the difference in buoyancy force.
Does the difference in density mean that you can like apply a greater pressure onto the?
Yeah, that's a good question. I suppose maybe I would think viscosity maybe would have a bigger effect in that, and it doesn't change the viscosity. But yeah, I mean, if you're pushing from conservation of momentum, if you send a heavier thing that way at a certain speed, then it sends you faster that way. I don't know how much that effect is, though. Okay, but we're going to use these values. And so there's the surface of the ocean. The pressure here, this is the pressure at our higher point, and this is just atmospheric pressure, so this is 1.01 times 10 to the 5th pascals. And then way down under the water is this box. That distance is not drawn to scale. And this is our P at the lower height. And so this equation says the pressure at the lower depth is equal to 1.01 times 10 to the 5th plus 1 times 10 to the 3rd, the density of water, times 9.81 times the depth, the distance in the difference in height, 3,800 meters. And so the absolute pressure at that lower point is 3.7 times 10 to the 7 pascals. How many times atmospheric pressure is that? So we're just going to take 3.7 times 10 to the 7 divided by 1.01 times 10 to the 5th. And this is about 366 times atmospheric pressure. Okay, so now we're going to think in terms of forces. So let's think of the wall on the right side. Okay, so what forces are acting on this? There is a force coming from the pressure on the inside going that way, and there's a force pressing this way from that outer pressure. The inner pressure is, this is still a really big, this force that atmospheric pressure is going to be applying, trying to blow this thing outwards, is still going to be a really big force. So I'm going to call this force from the inside positive, and I'm going to call this one negative. I guess I can just, yeah, I'll do that. So the force from the inside, remember that the definition of pressure is the force divided by the area. Okay, so you can turn that around and say that the force on this wall is equal to the pressure times the area. And so F in is 1.01 times 10 to the 5th times an area of 1 meter squared. And so we have 1.01 times 10 to the 5th newtons. That's a lot. That is, let's see, 1 times 10 to the 5th. That's about 25,000 pounds of pressure. And now the force from that outer pressure is equal to 3.7 times 10 to the 7 times 1 squared. So 3.7 times 10 to the 7 newtons. And so the net force pushing in on this wall is 3.7 times 10 to the 7, call that negative, plus 1.01 times 10 to the 5th, and you get basically 3.7 back, 3.69 times 10 to the 7 newtons pushing in.
You mean two?
No, because this is we're adding.
Oh, got it.
So what we have is that this is a tug of war between these two forces. Well, not the opposite of a tug of war. It's a pushing contest between these two forces. And one of them is 370 times bigger than the other one. And so the result is, you have 37 million newtons of net force pushing in, which explains why it's such a major engineering undertaking to make a vessel that can withstand these forces.
And so whatever the sealed pressure in the vessel is, that's the force being applied in every direction.
Yeah, perpendicularly at every point. Well, it's not the force, so if you think of, so imagine like a round thing, and then let's simplify it by turning it into tiny hexagons like a soccer ball, on each one of those hexagons, the force pushing out is perpendicular to the face, and the magnitude of the force is the pressure times the area. So calculate the area of that little thing, and that's the force pushing out there. It's easier to do it, with simpler shapes like squares and stuff. To do it with spherical things or cylindrical things, you'd have to use calculus, three-dimensional calculus.
What would change that to where a pressure is not being exerted evenly on all surfaces? If there's like an object inside the box?
The magnitude of the pressure is the same, but the direction changes as the perpendicular direction changes. That's what makes it complicated to do on a spherical thing, But yeah, nothing changes the magnitude of it, as long as the fluid is at rest in there. If there's fluid flow in there, it gets more complicated. Okay, any questions about that? There are two main ways to measure pressure. The first one is called a manometer. And that's used to measure the pressure of an enclosed fluid. So there's a reservoir over on the left in this, and then a tube like this. And inside the tube, you have a liquid with a known density. This can be water. Mercury is used pretty often. Alcohol is used. Over here is the fluid whose pressure you're trying to measure. The shaded area is a different liquid. And at the top, this is open to the environment, so this is atmospheric pressure. And this difference in heights here is what we're going to call H. And so the pressure in the enclosed fluid is equal to atmospheric pressure plus the density of the liquid times 9.81 meters per second squared times H. So this is a setup that you use if you want to measure the pressure in a fluid that you have contained. The other common device for measuring pressure is for measuring atmospheric pressure. That's a barometer. So this is used to measure the atmospheric pressure. And this is a 2D drawing of a three-dimensional thing. You can imagine this basin here. If you look from above, this has like a round or a square cross-section, and you just have a liquid in this basin. And then this liquid can climb up this enclosed tube, and it'll climb some distance up this. And this tube is sealed off from the atmosphere. The only pressure you have in here is the vapor pressure. That's the pressure of molecules that are leaving the liquid. It's basically like a boiling pressure, although this is below its boiling point. But if you think of what happens in boiling, molecules at the surface get enough energy that they fly out of the liquid. That's what causes a vapor pressure here. But people purposely use a liquid with a low vapor pressure that's close to zero. So usually you can just approximate this as zero. Pushing down on the liquid in the basin is that atmospheric pressure. And the distance h in this case is the distance between the liquid level in the basin and the liquid level in the tube. And so P atmosphere is just equal to the density of the liquid times 9.81 meters per second squared times that height. And so if you want really accurate measurements of the pressure of an enclosed fluid, you probably want to have a barometer in that room in addition to the manometer so you can get an accurate reading of the pressure in the room where you're using the manometer. Okay, because it comes into the calculation too. Okay, let me do a quick example problem. And then I'll stop and we'll do the quiz. So let's say that we have a barometer And let's say that we measure the height difference in this liquid as 0.55 meters. And the liquid that we're using is mercury. That has a density of 13,690 kilograms per cubic meter. That's pretty high. Steel is only 7,000. This is twice as dense as steel. And we want to know what the atmospheric pressure is. And so we have that the atmospheric pressure is the density times 9.81. I'm just doing everything in SI units. Times 0.55. And you get 73,864 pascals. Quite a bit lower than standard atmospheric pressure. Maybe this would be a pressure that you would take at a pretty high altitude.
In a storm?
I don't think it goes that low in a storm, but yeah, it does definitely changes in pressure
Storm in
correspond to, yeah, right, exactly, yeah.
Is an extremely high atmospheric pressure the sign of a tornado or an extremely low one?
I do not know.
I think part of what causes it is the difference.
I think, actually, I think for weather to come where you are, you always pretty much need to be at a low pressure because otherwise your high pressure keeps everything else away from you, you know. So my guess is that it's a low pressure that sucks those winds towards you, you know, but I'm not really a meteorologist.
And so the more dense the liquid, the more pressure is required to move it?
Yes, that's correct. Any other questions about that? Okay, let's stop there.